So, we have been discussing about different advanced surface characterization techniques for the last 4 or 5 even more 7 lectures. So, the last technique which I am going to discuss in detail is known as secondary ion mass spectroscopy. In the literature it is always written as SIMS, being the acronym for secondary ion mass spectroscopy. This is very advanced technique and very few laboratories in India have access to this technique. As far as I know, only the laboratories access to the atomic energies like BRC or IGCAR, they have access to these facilities. But still, for the understanding of different students, we need to discuss this technique in detail. The literature is very well known in these topics. The most important book on which literatures are available I have listed at the bottom. First one is by J.C. Wickerman. Second one is again the Encyclopedia of Material Characterization, edited by Bundle and Evans and Wilson. These two books are easily available in different libraries, so you can have access. The outline of this presentation is as follows. First, I am going to discuss about historical background of SIMS, but before I discuss about historical background of SIMS, I must talk about the mass spectroscopy per se. Then I am going to talk about the difference between the MS and the SIMS, and most notably what are these two techniques are, so that you can get a feeling of mass spectroscopy and secondary ion mass spectroscopy. Obviously, these two techniques are related. Followed by, I will discuss the working principle of both the techniques, and then I am going to talk about different measurements which can be done by SIMS. Also, lastly, the advantage, disadvantage, and some amount of instrumentations. As you know, it all started in about 110 years back by Sir J.J. Thomson, who first basically built the prototype of mass spectroscopy to measure the m by z of any electron, mass by species charge. And as you know, he was awarded Nobel Prize in 1906 for his discovery and for many other things which he has made. But basically the first concept of mass spectroscopy came into practice by a gentleman known Francis Aston, who was working in Cambridge in England, and he actually first principle or concept of mass spectroscopy was put forward into practice by him, and he was also awarded Nobel Prize in the year 1922. Then it saw a huge effort to make the mass spectroscopy popular. Different kinds of mass spectroscopic techniques came into picture, but the real problem in dealing with mass spectroscopy was the vacuum systems. In early 20th century, basically 1910 to 1930 and 1935, the vacuum technology was not so well known. So the technique has not progressed much. Only in 1948 to 52, in the post Second World War era, the important time of flight mass analyzer came into picture and changed the scenario. It was followed by a major discovery again by W. Paul, which led to quadruple ion filters. And this quadruple ion filters actually has allowed us to measure this PCS of different mass by Z value, m by Z values, and because of this very famous discovery in 1955, W. Paul was awarded Nobel Prize in 1989. Actually, he also invents ion trap in 1983 for informations. After that, in 1968, it saw the development of tandem mass spectrometers, and secondary ion spectroscopy came little later, at about 1980s, when the secondary ions production was possible by different primary ion sources. To give you a better idea of SIMS, the most important problem in developing SIMS was the pumping technology, vacuum technology, as I told already, and that is actually hindered the growth of these SIMS. In fact, only in 1940s, actually 1948 or so, the first prototype experiments in SIMS was done at University of Vienna, Austria. In 1960s, two SIMS experiment was developed, but not so good. One was an American project for analyzing moon rocks, other was at the University of Paris. These first experiments were based on a magnetic double focusing Richter field mass spectroscopy and used argon as a primary ion beam. Obviously, these things are not known to you, I am going to discuss in detail. And then this was followed by recent development on focusing these noble primary ion sources, species like C60, even ionized clusters of gold and bismuth. And this followed a lot of instrumentation and the computation of the technique, and now it is fully automated and comes at a cost of about few tens of crores of rupees. Well, what is actually mass spectroscopy? That is, you must know first. Mass spectrometry or mass spectroscopy is basically an analytical technique as any spectroscopic technique, but it measures a different thing. It measures mass to charge ratio of any charged particle. You must remember this. Any mass spectroscopy does not measure mass, it measures mass to the charge ratio of any charged species. So therefore, in any sample, whatever material you think of, there is no charged species because samples will be neutral. You need to create the charged species first, and then by using certain technique you can measure this mass to charge ratio. This is a characteristics of any charge, whether it is a single ion, single atom ion charge, or it is a multiple ion charge, multiple species charge, does not matter, but this is a very characteristic things. It have used in both quantitative and qualitative analysis to determine the composition, also structure of specific compounds. Not only that, it allows us to be used as an analytical method to measure the molecular and atomic weights of the sample. So it has a versatility, as you can see. It gives a host of informations, and I have listed only few of them in this slide. First and foremost, it allows us to determine the chemical and structural information of any molecule. Any molecule or any ionic species you see, it gives us an understanding of chemical and structural nature of that molecule. Then it allows us to identify the unknown compounds to start with. It also allows us to quantify the known compounds. We can actually determine the relative abundance of isotopes and measure the exact masses. Remember, it is possible to measure the exact mass of the isotope. Those masses you see in the books reported are basically measured using SIMS. And then it also allows us to measure the molecular mass of any sample, correct. Now if you look at the uses, it is used in wide spectrum irrespective of different branches of science and engineering. Most important one, it is used in geological problems, basically in oil consumptions or oil production units. Like, you know, in oil production unit there are different kinds of chemical species available, organic, and it allows us to detect them. Then comes the pharmaceutical industry, that is pharmacokinetics, drug discovery, drug mechanism. Next one which uses this technique extensively is space application, like composition of the plasmas and the solar winds by the astrophysicist. Obviously it can be used for environmental technique like water quality, food contamination, biotechnology. In fact, it can be used in high vacuum system, smart spectrometers to be used to measure even residual gases present in a particular systems. If you look at this series, I have not mentioned about materials science. So obviously material science is involved in all these things. We can use this particular spectroscopic spectrometry technique for analyzing our day-to-day materials or the materials which you are actually preparing in the labs in detailed manner. Well, so basically after knowing this mass spectroscopy and the advantage and that these things, what actually a mass spectrometer needs to have? What are the basic things it must have? Well, basically it must obviously have a sample, because that is what we are analyzing, and then we have to have a source of ions. So sample is ionized and we create different sources of ions. This is what is done by these techniques which I am going to discuss. And then these ions are actually analyzed based on mass to charge ratio by using either quadruples or time of flight measurements, and then they are detected either a photographic plate or electron multiplier or Faraday cup, or different kinds of detectors available. And the whole system, whole thing is kept, this whole thing has to be evacuated, because the ions needs to move forward from the source to the detector. So their movement should not be hindered by any kind of residual molecule, gaseous molecule present in the system. So vacuum systems to be of the order of create a vacuum of the order 10 to the minus 9 to 10 to the minus 10 torr inside the chamber, and this all actually leads to the cost of the instrument. So this is the basically 3 modules of any mass spectroscopy. In SIMS, both the analyzer and detector remain same, only thing which gets changed is the source. We do create secondary ions using the primary ions, okay, but in a mass spectroscopy we use primary ions to analyze these masses. So in a nutshell, if I have to show you in a very chart, what you need is to create ions, and this can be done by ionizations. You can do by electrospray, you can do MALDI, I will tell you. You can do even other ionization techniques, like you can use a primary source of ion, a sputter, and create ions. And then after you created the ions, you have to collect the ions. You collect the ions and then you separate them in a different mass to charge ratio. That is what is done by mass analyzer. It can be MALDI time of flight, or it can be quadruple time of flight, it can be quadruple time of flight only, or you can be triple quadruple also. There are many others actually, but these are the main ones. After that we will detect the masses, and that is done by mass spectrum analysis. Also you need to have a database, like X-ray diffraction has a database and many others. So this is the main thing of a mass spectroscopy. Only thing, as I said, is going to change in SIMS is basically this part. These 2 parts, other 2 parts will remain same. So actually you create an ion source, you can have a gas ion, mass analyze and detector. This is what I have told. So in a basically pictorial things, I can say there is an ionizer and there is a mass analyzer, there is a detector. That is how the ions actually move through this. How do you ionize actually? That is what we must know. There are different ways of ionizing. First one is known as fast atom bombardment, or FAB. This is nothing but impact of high velocity atoms on a sample dissolves in liquid matrix. If you have a high velocity atoms like argon or oxygen or cesium, and these atoms actually are allowed to fall on a sample which is kept inside liquid matrix, it can create ions of the atoms in the sample. Second one is secondary ion mass spectroscopics, and this is the topics of today's discussion. It is nothing but impact of high velocity ions on a thin film of a sample of a metal on a metal substrate. It can be also dissolved in liquid matrix. So by this way, these fast ion bombardment and secondary ion mass specs, actually the preparation of ions are almost similar. What you need to have is impact of the high velocity ions in case of SIMS, and in case of fast FAB you need to have impact of high velocity atoms. Then you can always have a plasma desorptions. This is nothing but impact of nuclear fission fragments. Nuclear fission fragments are always like alpha particle, gamma particle or beta particles. These fission fragments can lead to plasma desorptions. You can also have a technique known as, so we have discussed this, we can also have a technique known as matrix assisted laser desorption and ionization, which is known as MALDI. That is what I talked in the last slide. So it does actually create ions by impact of high energy photons on a sample embedded in a solid organic matrix. So, you create a photon is nothing but h nu, laser has a lot of photon or quanta, and this is basically allowed to fall at a high velocity on a sample which is embedded in a solid organic matrix, and that is how you can ionize ions. Then one can do field resorption on electrospray. Field resorption is nothing but imposition of high electrical field gradient on a sample deposited in a special solid substrate. Those of you who have some idea about atom probe, in an atom probe we do the same thing actually. We just create a large, we impose a high electrical field between the sample and another electrode, and because of the creation of the high electric field, the ions on the sample is just dislodged, or the atoms in the sample are dislodged and created comes as an ion. Electrospray is basically very simple, much simpler than all these techniques. It is nothing but a formation of charged liquid droplets from which ions are desolvated or dissolved. You have a charged liquid droplet, you can create charged liquid droplets by using electrical field or just spray using electrical field, and then you can dissolve it or dissolve. So, these are the different techniques of ionizations which is done. So, you see SIMS comes one of the techniques of ionizations, not only SIMS, there are many other techniques. So, that is why I want to discuss mass spectroscopy in togetherness. Now, how do you then, after creating the ions, you have to analyze the masses. How do you analyze the masses? There are host of techniques available, that is what the discoveries happened. First and very simple one is single focusing magnetic deflection, which I will tell you. Second one is double focusing magnetic analyzer. Third one, which is widely used, is quadruple mass analyzer. Then you have mass analyzer, and the last one, which is very popular one, is known as time of flight mass analyzer. Let us look at them. This particular slide is on single focus mass spectrometer. This is very simple technique, very simple technique. This picture schematic is taken from this one. There is a presentation available on the website. What is done here? Let me first explain the theory. This is the most common type separator. At any given accelerating voltage V, suppose, all the singly charged ions are provided some kinetic energy, and that is given by this electronic charge E multiplied by the accelerating voltage V must be equal to kinetic energy of the charged species, that is half mv square. Now, if you allow this charge accelerated species to pass through a magnetic field, which is shown here, this is the magnet, you see, the charged ions will experience a magnetic force, and this magnetic force is given by HeV, where H is the magnetic field strength. So, therefore, this is balanced, this magnetic force is balanced by the centrifugal force, obviously. So, that means we can write down HeV must be equal to centrifugal force, that is mv square by r. So, you get m by E is equal to h square r square by 2v, straightforward, and this is what is the classical equation which allows us to separate different PCCs with different values of m by E ratio. As you can see, depending on the different m by E ratio, if you keep h and v constant, r will change. So, therefore, lighter ones will come as a smaller r, and heavier ones come as a very large r. So, that is how actually you can differentiate between different PCs, charge PCs with different m by E ratios. It is very simple actually. In fact, the first you charge, then accelerate, and then accelerated charge are passed through the magnetic field and it separates out. That is how it is done. So, we are focusing with a single magnets, that is why it is called a single focus mass spectrometer. Remember, this is actually how we can actually separate the ions very easily, and subsequently what all techniques, several techniques you will see, they are actually modification of this one. So, it is very high resolution, its instrument gives actually, it gives you quite substantially high resolutions in the sense of ppm level detection possible. In this type of instrument, two ion beams from independent sources passes side by side to a common mass analyzer and detected by separate collectors. This is used to compare sample with a standard array through different ionizing condition. Resolving power is order of 30,000 sorry. Such resolving capability enables high molecular weight fragments which differ only by one mass unit. That means if there are two PCs with a mass unit difference of 30,000 and 29,999, still we can detect by this. That is what the resolution of this instrument. Next one, which is also widely used quite some time, is known as double focus mass spectrometer. What is double focus mass spectrometer? Well, single focus mass spectrometer you have seen, here we are using two focusing magnets. So you have you can see this is the lens, and then basically ion sources come through this is the ion source, and then it passes through a lens, there is a source slit, and then there is a magnetic field, it just basically magnetic sector, it just separate these ions out or filters the masses, and then it passes through this single mass whichever is basically passing through this radius which is matching with the slit will pass through to go to the detector. So if you change the slit little bit, or if you change the magnetic moment, that is H value, you can allow either this one or this one or this one to pass through the slit and be detected. That is the advantage as compared to the first technique, the single focus mass spectrometer. It has very much better resolution than the single focus mass spectrometer. That is mainly because there is an extra element like this possible here. That is why it is called a double focus, because first you are focusing with the magnetic sector, then you are focusing with the electrostatic sector, and that is how actually you can detect very precisely each and every atom charge pieces. This is again taken from one of the websites which is available on the internet. Next one, and probably one of the best one, is quadrupole mass analyzer. The reason I am saying this is the best one, because it allows us even better measurement than single focus or double focus magnetic spectrometer. Well, it makes use of a combination of direct current and rare frequency electric field applied to 4 parallel rods. Remember, it is applied to 4 parallel rods to separate ions according to their mass by charge ratio. So we are using direct current as well as rare frequency electric field and using 4 parallel rods. These are all, that is why it is called quadrupole, to separate the ions. What is done here? This is taken from Wickerman's book. So you have a sample, you create ions by different ionization techniques, and then you have 1, 2, these are actually filters, okay, post or P filters quadrupole. They are the 4 important ones, and then it passes through this region where this quadrupole actually separates the ions depending its mass to charge ratio and detected. You can see here this is DC voltage, this is the RF voltage you can apply, and repeat, these are the 4 probes of different dimensions. Now if I plot the movement of the ions, you can see here this has the 2 parameters A and Q. Q is the charge and A is basically the distance between the quadrupoles. So if you can see the plots, you see here there are different regions. This is U by B constant, low resolution, U by B constant, high resolution, okay, U by B, U and B. This is U minus delta U by V constant by constant resolutions, and this is what is the region of stability. So that means we can change U and V in such a way, U is basically DC voltage and V is the RF voltage magnitude. So by playing around these two, we can actually get into this region of stability, and that is the region one which you need to work. Obviously, if you want to work with U by V constant high resolution region, you can do that, or you can want to work with constant resolution, you can do that depending on the systems on which you are working on. So, as you see here, this gives us many possibilities of changing the conditions and do the measurements. Fourth technique which is important is ion trap mass spectrometer. As the name suggests, is basically traps. As you know, Paul actually got Nobel Prize because of ion trap mass, the technique availability. I have told you that in 1983. Ion beam currents are normally of the order of 10 to the minus 15 to minus 19 amperes, so very small. That is because the number of ions present in the source beam is very small. This technique generally employed ion collectors, and they are actually photographic plates or electron multipliers. So, what is done here? You have basically filament, and which actually creates ions, a charged species, and then we have this kind of ring electrodes which basically collects or traps these ions, and after that we can actually use this mass spectroscopy or use this kind of single focus or double focus or quadruple, and then we can actually analyze these ions by mass by charge ratio, and finally we can detect them using transducer. That is why we did. So, basically preparation wise is different, distinctly different from the other three techniques. This is normally not used much except for few specific applications. This one is also taken from this website. Well, the last technique which I am talking about is what is known as time of flight mass spectrometer. The schematic shows the technique actually. What is here? You look at it very carefully. You have an ion gun which creates or ionizes the pieces, and then there is a pulsing action. It can pulse actually, ion gun can obviously pulse like a laser beam, and then you can focus this. It also allows, the ion gun also allows to raster like SEM the ions, and then once it falls on the target, it creates ions from the surface, and then it passes through this extractor which extract the ions which are coming from this, because of this ionization due to ion gun. That means we are creating a secondary ions actually, and then basically ion mirrors, which is nothing but a quadrupole detector or maybe a time of flight detector. It basically separates the ion, and detector detects and gives you the spectrum. Correct. So, many cases as you create more ions, so you have to have an electron flight gun, otherwise charge balance will not be there in the sample surface. In a more sophisticated design, the time of flight analyzers corrects for the small differences in initial energy and angle in order to achieve high mass resolutions. It is a combination of linear drift paths, electrostatic sectors or the ion mirrors which are used, and results are actually comes with the mass resolutions of above 10,000 can be achieved. Advantage of this technique about the quadrupole and the magnetic sector type is that extremely high transmission, parallel detection of all masses, and unlimited mass range is possible. Yes, because it does not use, because what we are doing is basically time of flight measurements. How much time a mass takes to fly or move in a particular distance, and depending on that we can differentiate among different species. We are not using the exactly m by z ratio. So, let me just give you the mathematics of it. Pulses of secondary ions are accelerated. As you know, ion gun creates secondary ions, and pulses of secondary ions are accelerated to give to a given potential which is of the order of certain kilo electron volt 3 to 8, such that all the ions possess the same kinetic energies. Then these ions are allowed to drift through a field free space. Remember, after these ions are accelerated secondary ions, they are allowed to pass through a drift through a field free space. We are not applying any magnetic electrostatics field before reaching a detector, and when it passes through, because they have the same kinetic energy m by mv square, but velocities will be different. So, because of this, masses are different, velocities will be different. Because of this, the time it takes to move a length will be given by L m by 2 z v half. L is basically the length, path length, flight path length, m is the mass, z is the ionic charge, and v is the accelerating voltage. So, as you can see, depending on m by z values, if even L and V are constant, T will be differed, and by knowing the different times we can actually separate these ions very easily. This is actually widely used now for the whole worldwide technique, and it has many advantages. Now, if I go back to the previous slide, that is what is done. In the ion mirror, between the extractor and ion bearer, what is done is that this secondary ions having a same kinetic energy travels or drifts to a path of certain length may be this much, and gets separated out. And then we can plot, I will show you the plots also later, we can plot and get idea of that. So, this is I am going to discuss in detail when I come to SIMS. So, but to give you some idea, in a static SIM experiments, it actually analyzes the original non-modified surface compositions, uses time of flight measurements, and it basically is a quasi non-destructive surface analysis because it uses very low ion dose. Well, as I have talked about a lot of different magnetic focus, like single mirror magnetic focus or double magnetic focus or even quadrupole, let me just give you some idea about what a radius of curvature means, how does the ions actually get curved. Radius of curvature are of any ions of distinct m by z ratio travelling through a perpendicular magnetic field B after it has been accelerated by certain potential is nothing but 1 by B within bracket 2 m v by z to the power half. So, if B is constant, V is constant, it depends on the m by z. So, the travel ions actually travelling, as I go back I can ions which are travelling at different radius, that will depend on m by v. So, that is what actually used in this technique. Now, after giving a huge introduction, lot of things I have talked about it, about the mass spectroscopy. Let me just get into details of the secondary ion mass spectroscopy. Although there are many things which are similar, but distinct things, the things which are distinct in SIMS as compared to this MS or mass spectroscopy is to be known to you very clearly. SIMS per se is a surface analysis technique, remember this. Mass spectroscopy may not be surface analysis technique. SIMS is basically a specifically surface analysis technique. It is used to characterize surface and subsurface regions of any material. That is actually what makes SIMS very popular. Even if you have a thin film on the surface of any material, you can analyze it to the precision of SIMS. It can give you ppm level precision. It effectively employs the mass spectrometry, what I discussed, of ionized particles which are emitted when a solid surface is bombarded by energetic particles. The schematic diagram on the right side or to you is showing this picture. We have an